Here we're going to continue our discussion about phase equilibria. In particular, we're going to consider the detailed thermodynamics of Raoult's law. Now, if you remember from last lecture, we decided to study phase equilibria, and we said that typically what one does is make a pressure-temperature diagram and put on points of interest like a critical point, triple point, gas, liquid, solid, liquid, and gas. And we consider that in detail for a single component. And we said for a single component, a single pure substance, we have 2 degrees of freedom. And we generalize this to the Gibbs phase rule, where the degrees of freedom is equal to the number of components minus the number of phases that you want to be in phase equilibrium plus 2. All right, and then for a single component, for C is equal to 1, and you want any phase, it doesn't have to be any phase equilibria. This implies that your degrees of freedom was equal to 2, and we said the 2 degrees of freedom are temperature and pressure. We can independently specify temperature and pressure, and once we specify those, then we know what the phase is. So phase equal 1. If, on the other hand, we have a single component and we want the number of phases to be equal to 2, for instance, liquid and solid to coexist, that means that degrees of freedom equals 1, and so on. Well, now in this lecture, what we're going to consider are 2-component systems, where you have just not a single pure substance, but now you have 2 components. Well, the degrees of freedom for this system are the number of components, which is 2, the number of phases. Let's take in general, we have 2 phases, 2 phases that can exist anywhere. We have 4 minus the number of phases. So if we just want a single phase, we're not going to put any phase restrictions, then the degrees of freedom will be 3. So here we have 2 degrees of freedom. This is the x and y axis. Now with 2 components and no phase equilibria, which means that the number of phases can be equal to 1, so we have no constraints, then the degrees of freedom will equal 3, so really what we need is a 3-dimensional graph. So along one axis will be pressure, along the other axis will be temperature, but that third axis, this will be, say, mole fraction of the first component, or it could be mole fraction of the second component. You don't need a fourth axis because the mole fraction of the 2 components have to sum to 1. So in general, for 2 components, we need a 3-dimensional graph. So typically what one does is to plot it at constant temperature, which corresponds to planes intersecting the temperature axis. And therefore you have a 2-dimensional graph, pressure versus composition, and usually it's the mole fraction of some substance for substance. Or you can have constant pressure that corresponds to planes across intersecting at right angles with the pressure axis. In that case you would plot temperature versus composition. So you have pressure composition or temperature composition. Now for the first part of this considerations, where you have 2 components, we'll consider pressure composition graphs. So now, so in general, that's what we'll have. We'll just have slices in this 3-dimensional graph where you have 3 degrees of freedom. We'll restrain 1 of the degrees of freedom. We'll get rid of it by saying constant temperature, pressure, and therefore you have these 2 graphs. Now, if we want to put in a phase equilibrium, typically 1 and 2 here, the subscripts 1 and 2, represent the 2 components. And this is the chemical potential in phase 1 of component 1 will equal the chemical potential of component 1 in phase 2, and a similar expression for component 2. So now these are constraints, And if we put these constraints in, equilibrium for phase diagrams, we're going to reduce the degrees of freedom. Okay, so let's see in more detail what we're talking about here. Suppose we have a sealed system here, and let's take a single component, and this will be a liquid. All right, so here we have a single component. We'll denote that with the 1, which we're eventually going to put as a subscript. And this will be in the liquid phase. But as we know, at equilibrium, the liquid will be in equilibrium with the vapor. It'll have a certain vapor pressure. Liquids usually have vapor pressure in the gas phase. So if we want phase equilibrium for a single system, remember we're going to reduce our degrees of freedom by 1. So instead of a two-dimensional plane, we now have just a single line we have to follow. We said that the chemical potential of component 1 in the liquid phase at phase equilibrium has to equal the chemical potential of component 1 in the gas phase. This is at phase equilibrium. All right, now let's develop this. Let's look at thermodynamically in more detail what's happening here. We're just looking at the single component, and then once we understand that, we'll add another component here. All right, so the chemical potential of component 1 in the liquid phase will be the chemical potential of component 1 in the liquid phase, standard state, plus RT times the natural log of the activity of component 1 in the liquid phase. The same way with component 1 in the gas phase, that's equal to the chemical potential of component 1 in the gas phase, standard state, plus RT times the natural log of the activity of component 1 in the gas phase. All right, now as we said, for condensed phases such as water liquid or water solid, for solids and liquids, the activity of the condensed phase, which we have, if we're just looking at the liquid, that's a condensed phase, and we have a single component, so it's pure. The activity of the liquid phase, in this particular case, we have a single component, will be equal to 1. And the activity of the gas phase, remember the activity, let's say of component 1, the gas phase, that will be equal to the pressure in the gas phase divided by the pressure at some standard state times some fugacity constant for the first one. Let's assume that we have an ideal solution so that this is just the pressure of component 1 divided by the P0. That's what the activity is. Should be subscript 0 for standard state. Sorry about that. And let us denote further that the substance, we'll put a star up there. That star means that we're doing a single component, and the single component is pure, so this will be the vapor pressure of the pure component above the solution. So that's what that is. Vapor pressure of the pure component. That's what that star means there. All right, so we have an expression for the chemical potential in the liquid, the chemical potential in the gas phase, and at phase equilibrium, the chemical potentials are equal. All right, so with that, let's equate these two. At equilibrium, they're equal. So on the next page here, we'll equate those two. So the chemical potential of liquid is the chemical potential of liquid in the standard state. So you note that, this term goes to 0. So the chemical potential of liquid is the chemical potential of standard state. Well, that sort of makes sense because it's a pure substance. And so that is equal to the chemical potential in the gas phase. So this is component 1 in the liquid phase, component 1 in the gas phase, standard state, plus RT times the natural log of the vapor pressure, the pure substance, divided by the standard state pressure. All right, that's interesting. It relates the chemical potential of the liquid, standard state chemical potential liquid, to the standard state in the gas, plus this sort of correction term because you don't have the vapor pressure above the liquid to be equal to the standard state 1 atmosphere usually. All right, so that's, remember that equation, that'll come in handy a little bit later. Now we're going to extend the thermodynamic analysis now to two components. All right, so let's draw a picture there. Picture's worth 1,000 words. Okay, so here's our box. We'll have component 1, which is an equilibrium in the liquid. Here's component 1 in the gas phase. We'll now have a second component, which is a liquid down here. This will also be an equilibrium with component 2 in the gas phase. Okay, so what we have now with these two components is that the chemical potential of 1 in the liquid phase is equal to the chemical potential of 1 in the gas phase. That's at equilibrium. This, by the way, is at phase equilibrium. Okay, and chemical potential component 2 in the liquid phase will be equal to the chemical potential component 2 in the gas phase. That's what we mean by phase equilibrium. Now, well, just let's go ahead and put some expressions in here. So let's just do it first for the component 1. So the chemical potential component 1, sorry, that shouldn't be a 0. And let's just do the liquid phase here. In the liquid phase, that'll be the chemical potential of 1 in the liquid phase, standard state, plus RT times the natural log of the activity of 1 in the liquid phase. Now for a pure component, the activity was 1. But now since we have two components, the activity in the liquid phase is no longer 1. In fact, it's the mole fraction of 1, we'll find out, or we already know. And then the chemical potential of 1 in the gas phase is a chemical potential of 1 in the gas phase at the standard state, plus RT times the natural log of the activity, but just let's go ahead and assume we have ideal solutions and so on, the pressure divided by the standard state pressure. Now this is no longer the pressure, the pure component. Why? Well, it's not a pure component anymore. We have two components. So this differs from what we developed before. However, we do know that the chemical potential of the standard state chemical potentials of the liquid is the standard state chemical potential of the gas plus this. So this for standard states here, and this is a pure substance. So we can go ahead and substitute in for this standard state chemical potential of the liquid into there, and then of course at phase equilibrium we're going to equate these. So let me go ahead and substitute in for there what we had the expression on the other one, so that the chemical potential of the liquid in standard state is the chemical potential of component 1 in standard state plus RT times the natural log of the pressure of 1, pure 1, vapor pressure of pure substance divided by the standard state, plus RT times the natural log of the activity of 1 in the liquid state. So we just substitute in what the standard state for 1 liquid was. That's what that was. That is equal to the standard state chemical potential of 1 in the gas phase plus RT times the natural log of the pressure in the mixture, not the pure substance, but the mixture, divided by the standard state. How convenient these cancel out. Let's put, let's see, let's put this term over there. So we have RT times the natural log of the activity of 1 in the liquid phase is equal to RT times the natural log. Let's see, I have this one and I'm subtracting this one, so it'll be P1 over P1, P0. That's what that is, but when I subtract that, that will go down in the denominator. So this would be P1 star divided by P0. Well, the P0s cancel out. So this is just equal to RT times the natural log of the pressure above the solution in the mixture divided by the pressure above the solution in the pure state. That's the star there. And if RT log of A equals RT log of this implies that the activity of substance 1 in a liquid phase is equal to the pressure of 1 divided by the pressure of 1 if it were pure. So if you have pure substance, the vapor pressure, the pressures here will be equal, the activity be 1 for a pure liquid. And if you have less than 100%, if you have less than pure substance, you dilute it out by adding something else, and the vapor pressure goes down, and the activity will go down just by this ratio. All right, or let's rewrite this. So remember, we said that the activity of a liquid can be written as the activity coefficient. Let's continue using, say, component 1. So let's say the activity of component 1 in the liquid phase is equal to the activity of component 1 times the mole fraction of component 1 in the liquid phase. So this is mole fraction, it's concentration unit of component 1 in the liquid phase. So let's assume that gamma 1 is equal to 1, so we have an ideal solution. So the activity of component 1, the liquid phase, is just the mole fraction of 1. And we use X for mole fraction in the liquid phase. A little while along in this lecture, we use Y for mole fraction in the vapor phase. So this is the liquid phase. So if that's true, okay, look at this. We can just replace that. So the mole fraction of 1 is equal to the pressure of 1 above the solution, which has two components, divided by the vapor pressure of pure A, or pure component 1. And this is the actual pressure, above mixture. So what does this mean? This means this is a solution concentration. The solution concentration, mole fraction, governs the ratio of the vapor phase, the pressure, the partial or the fraction of pressure in the vapor phase. Or another way to write that is that the pressure above a solution is equal to the mole fraction in the liquid, not above the in the solution, times the vapor pressure of pure solution. This is known as Raoult's law. Raoult's law. And usually that is just given to you in introductory chemistry, but here we derived it using the fact that we had phase equilibrium. Well, that's kind of neat. So let's go touch base with our slides here. So where are we? Yeah, so for two liquids, each having a vapor pressure, so I'll show you the figure in the next slide, we have Raoult's law. Okay, so just let's look at this. All right, let's go a little bit further. Let's go where no person has gone before, except a million other people who have studied PChem. Let's assume we have ideal gases, so we can use Dalton's law. So Dalton's law says the total pressure in a mixture of gases is equal to the partial pressures, and we just have two components, so it'll be the partial pressure of component 1 plus the partial pressure of component 2. That's okay for ideal gases. So we know that the partial pressure of component 1 is the mole fraction times the vapor pressure of pure component 1. And you could just go through the same derivation and substitute 1 or 2 for 1, and you get this, the mole fraction of 2 times the vapor pressure of pure 2. So, anything we did here for 1, just change a 2 and you'll get the exact same thing. All right, we know that the mole fraction of 1 plus the mole fraction of 2 will equal 1. So let's get rid of mole fraction 2. Mole fraction 2 is 1 minus mole fraction 1. So the total pressure can be written as mole fraction 1 times the vapor pressure of pure 1 plus 1 minus the mole fraction of 1 times the vapor pressure of pure 2. Or the total pressure is equal to the mole fraction, the vapor pressure of pure 1 minus the vapor pressure of pure 2 times the mole fraction of component 1 plus the vapor pressure of pure 2. So look, if you plot total pressure versus mole fraction 1, you should get a straight line, and we'll see that in just a minute. And if you plot the individual pressures, like the pressure of 1 versus mole fraction of 1, you'll get a straight line. And those kinds of straight lines that you get when you do those plots, if they're straight lines, then the solution follows Raoult's law. Okay, so let's take a look at a plot of those things. Here we have a plot of Raoult's law. Notice they're all straight lines. What we're plotting here is vapor pressure of A or B in the solution as a function, and this we're changing notation here. Sorry, I should have got another graph. A and B correspond to components 1 and 2 that we had in our derivations. But what you're doing is plotting here vapor pressure of A or B as a function of concentration of B or concentration of A. Note that A plus B, since there are only 2 components, they have to add to 1. All right, let's look at this. Here we have total pressure. And as we predicted, the total pressure is a linear function of the mole fraction. All right, so here's the mole fraction of B goes from 0 to 1. There's that linear function. That's total pressure. Let's look at individual partial pressures. Individual partial pressures just are linear, or proportional actually, with the proportionality constant mole fraction. So just let's take a look at that. So these are the individual pressures. Yeah, they're linear also. So when you see a plot like this, you'd say that the mixture you're looking at, the 2 liquid components, both of which have contribute to the vapor pressure above the solution, they follow Raoult's law. So let's look a little bit closer. So here we have the mole fraction of B is 0, and the mole fraction of A is 1. So here you have pure A. And out here, where the mole fraction of B is 1, here you have pure B. And this starts at 0. So when you have pure A, you have no B, so the line of B starts at 0. And you have pure A, so this will be the vapor pressure of pure A, which in our notation you put a little star up there. So there's a vapor pressure pure A. As you increase the concentration of B and decrease the concentration of A, the pressure of A decreases linearly all the way down to 0, where you don't have any more A and all B. And the pressure of B, which started at 0 when you didn't have any, will linearly increase all the way up to the partial pressure of B, or the vapor pressure of pure B. That's our star there. So that's how you would read a Raoult's law kind of plot. Important equation. Okay, so that's Raoult's law. Raoult's law says that the total pressure above a solution, or the partial pressure of each component above the solution, is linearly related to the mole fraction in the solution. So the vapor pressure above the solution is controlled by how much of that component is in the solution. What we're going to do in the next part of this lecture is to generalize this idea and plot not only pressure versus composition in the liquid phase, but also develop an expression for pressure versus concentration in the vapor phase.